Hello, and thank you for tuning into my talk as part of the application-oriented modelling stream of the MSM workshop. My name is Ryan Prosser, and today I'm going to be talking about quantitative lithium-ion diagnostics. This is a pre-recorded presentation, and details on how to submit questions will be given at the end of the video. So first, let me tell you a little about myself and my background. As I've already mentioned, my name is Ryan Prosser. I'm a final year PhD student at Imperial College London, part of the Electrochemical Science and Engineering group. I did my master's degree in mechanical engineering, also at Imperial, which I graduated from in 2017. My areas of research include degradation and diagnostics of lithium-ion cells, specifically trying to retrieve useful degradation information during normal battery operation. I'm also interested in estimation of parameters which quantify the extent of degradation and how they impact cell performance. And I'm also interested in linking the thermal behavior of cells to degradation. Today, I'll be presenting our group's latest work on diagnostics, led by myself, in which we developed a novel technique capable of diagnosing degradation modes under load. We will start with a very quick and simplified look at the diagnostic techniques found in literature. We will evaluate the diagnostic techniques based on two factors: ease of implementation and the level of degradation detail provided. The different levels of detail are capacity and power fade measurements, degradation modes, which are loss of active material, LAM, and loss of lithium inventory, LLI, and mechanisms, which are the likes of SEI layer growth and lithium plating. The ease of implementation categories are destructive, which is complete cell disassembly, ex situ, where the cell remains intact but is removed from its working environment, in situ, where the cell stays in its working environment but is subject to loads not typically seen in application, and finally in-operando, which are the cell's normal operating conditions. We then populate these axes with common techniques found in the literature. The techniques which quantify degradation are distinguished from more qualitative techniques by the solid lines and dotted lines surrounding the box. What's immediately apparent is there seems to be a trade-off between the level of detail and ease of implementation, and many techniques only offer qualitative insights rather than quantitative insights. A line can be drawn through techniques which are at the forefront of this trade-off, and we'll call these the state of the art. Advancements in the field will tend to push this state-of-the-art line further into the top right corner, that is, identifying a higher level of detail using conditions which are easier to implement in application. The new technique developed in this work aims to provide quantitative mode-level detail for in-operando conditions, which is ahead of this state-of-the-art line. In summary, there's a trade-off between detail and ease of implementation. OCV models are the state-of-the-art in quantifying degradation modes, but require in-situ conditions. This novel technique uses heat generation to quantify degradation modes under normal load. It has the same number of parameters as OCV models and is robust to the operating conditions such as cell temperature and C rate. The technique requires modeling and measurement of cell heat generation. Total heat generation for a cell can be represented by this equation: the sum of irreversible and reversible heat, as well as the heat of mixing and the heat generated by side reactions, which we assume are negligible. The irreversible heat is given by this equation and represents a heat generated by moving charge through a potential difference, that is, the overpotentials created by the various electrochemical processes in the cell. OCV can be modelled by some set of degradation parameters P, and voltage and current are measured. Here, red represent measured quantities and blue represents modelled quantities. The reversible heat, which is generated by changes in electrode entropy, is given by this equation. In the equation, du by dt can be modelled by the same degradation parameters P, and T and I are measured, assuming uniform cell temperature. The total heat generation can also be measured through the various thermal pathways that heat travels out of the cell. We can then form an optimization problem, which will aim to find the degradation parameters P, which minimize the difference between the measured and the modelled heat generation. We have now seen how we can parameterize OCV and entropy in terms of some parameter vector P. Now we need to determine what parameters make up P. As we know, the full cell potential is the difference between the cathode and anode potentials as shown in the figure. The shape of the full cell potential is determined by the cathode and anode capacities as well as their relative offset, which is labelled OFS in the figure. If we fix cell capacity, we can adjust the relative amounts of electrode capacity and the offset between them to change the shape of the full cell OCV. The lithiation fraction Z can be thought of as a state of charge for each electrode. As shown on the figure, there is an upper and lower bound on Z for each electrode, which is shown in the figure by ZPE up, ZPE low, and the same for ZNE. When we change the electrode capacities and their offset for a fixed cell capacity, we change these upper and lower bounds on Z for each electrode, and hence change the shape of the full cell OCV. Similarly, if we change these upper and lower lithiation limits, we change the electrode capacities and their offset, and hence we change the shape of the full cell OCV. Exactly the same logic can be applied to the entropy of the full cell. It too is equal to the difference between its half cell entropies. By changing the values of the lower and upper limits on Z, we can change the shape of the full cell entropy curve. And so we now know how to fully define the shape of the full cell OCV and entropy using the upper and lower lithiation limits for each electrode. Therefore, our parameter vector P is the 4 lithiation limits for the individual electrodes. If the electrode lithiation limits are known, it's very simple to calculate the electrode capacities and their offsets by simple geometric relationships found from the left figure. Once the electrode capacities and offset are calculated, the degradation modes can be calculated using the formula shown in the bottom right of the slide. Now that the cell heat generation is expressed in terms of parameters which can be used to calculate degradation mode amounts, the technique is ready to be tested. Here we evaluate the performance of the technique in estimating electrode capacities and offset amounts when compared to the state-of-the-art OCV method. First, we evaluate by eye how well the modelled heat generation matches the measured. Pictured here are 1C discharge and 1C charge datasets. We see that for the discharge case, we have a very good fit for both shape and magnitude. In the case of charging, the magnitude of the modelled heat generation is higher than the measured, but the shape is captured very well. When viewing the heat generation fit, the shape of the curve is more important than the magnitude, as the shape is determined by our cell stoichiometry, and magnitude can be easily influenced by experimental errors when measuring heat generation. We now see what capacities and offset the technique predicted, which are represented by the groups of 3 bars in the plot. On the very left, we have the state-of-the-art OCV method's predictions, and we assume that these values are correct. For the case of charging, it is seen that all parameters predicted by the technique are a very good match to the OCV method for all 3 C-rate cases. In the case of discharge, the offset and positive electrode capacities are very well predicted. The negative electrode capacities are not as well predicted as they are in the case of charging, but are still reasonably well predicted across all C-rate cases. So far, we can conclude that the technique performs very well for beginning of life cells and predicts the stoichiometric parameters with a high level of accuracy. We can also say that the technique is robust to several C-rates under both charging and discharging. Next, we'll evaluate the performance of the technique on cells that are degraded. We now examine the technique's performance for degraded cells in the same way. Again, we examine the heat generation fits. Here a 1C discharge and C/2 charge are shown. Beginning with charge, there's a very good agreement between the modelled and measured heat generation. Both shape and magnitude are captured very accurately. For discharge, however, we see that the measured heat generation has lost the characteristic peak and trough which was seen at beginning of life, and hence the shape is not captured accurately by the model. The parameters predicted for the degraded cells are shown in the bar plot. On the very left we have the beginning of life parameters, and immediately to the right of this are the parameters predicted by the OCV method for the degraded cell. First, for the 3 charging datasets, we see that all parameters are well predicted for all of the C-rate cases. For discharge, however, we see that the performance is poor, and between the datasets there is a high variability in the parameters predicted. For the degradation datasets, we then conclude that the technique performs very well for all charge cases, showing that under charge the technique is robust to C rate as well as levels of degradation. However, we see that for discharge the parameters predicted are not accurate. This is due to the model not capturing the shape of the heat generation well, as seen in the top left figure. Finally, we quantify the technique's performance in predicting degradation modes. The figure on the left is a copy of the figure from the last slide and is here for reference. The table shown gives the amounts of each degradation mode predicted by the state-of-the-art OCV method and by the charge cases for the new technique. Discharge is omitted from this table as its performance is poor, as previously discussed. Feel free to pause the video at this point to examine the numbers in more detail. However, I'll skip to the final two columns in the table, which give the mean error across all charge datasets, as well as the range of error. The mean error gives an indication of the accuracy of the technique, and the range gives a measure of the robustness of the technique. It is seen that the technique is excellent at predicting LAM for the positive electrode, and also the LLI, with very low errors and a very narrow range. The negative electrode LAM has a higher error and range, but still acceptable. The reason for the technique's slightly weaker performance in identifying negative electrode capacity is due to the entropy profile in OCV for the negative electrode being very flat apart from at low lithiation fractions. It should be noted that the OCV method also faces a similar problem when trying to predict negative electrode LAM. And so our conclusions from this slide: charging tests have a good accuracy and robustness when calculating all degradation modes, especially so for positive electrode, LAM and LLI. In conclusion, in this work, a diagnostic technique was developed capable of quantifying degradation modes. The specific benefits of this technique are that it can be done under load during normal battery use. It also has a low number of parameters, making it a strong candidate for onboard vehicle applications. The technique was able to predict degradation mode amounts with errors of less than 2% in all cases and less than 0.3% for positive electrode LAM and LLI. The technique was also shown to be robust for a range of loads, up to 2C and probably higher, making this a technique that would be suitable for fast charging protocols. The technique can also be improved for degraded cells under discharge. It is thought that by adding diffusion dynamics to the model, or by using more intelligent fitting algorithms, the technique's predictive powers for discharging data can be vastly improved. And that's the end of the talk. I'd like to thank you and congratulate you for making it all the way through to the end, and I hope you enjoyed. On the next slide are details on how to submit any questions you have on the talk to the upcoming Q&A panel session.